Okay, so we've just looked at the acid dissociation constant, but all the acids we've looked at so far were monobasic. In this case, I want to look at polybasic acids and what are the Ka values for polybasic acids. A quick reminder of what we mean by a polybasic acid. A polybasic acid simply has more than one acidic proton in. So sulfuric acid would be what we call dibasic or sometimes diprotic. Phosphoric acid has got 3 acidic hydrogens in, so this is tribasic, and hypophosphoric acid, which has actually got 4 acidic protons in, is known as tetrabasic. So this is all in contrast to things like HCl, which have only got 1 proton in. So how do we work out the Ka values for polybasic acids? So here's phosphoric acid as an example. So if you look up the Kas for phosphoric acid, you actually find there's 3 values. Now this is quite strange because these hydrogens are all actually identical. There's nothing different between these hydrogens, but somehow they have different Ka values. Now that's strange. Well, the reason for it is because each Ka value corresponds to a separate and sequential deprotonation of the molecule. Well, what do I mean by that? Well, separate, I take to mean that we have one H plus only removed. So in each of these cases, only 1 proton is removed. Sequential, because we're always going to start with a different species. So this is very much like ionization energies, and I hope you'll see the connection as we do it. So the first Ka value corresponds to this equilibrium here. I'm just going to write the molecular formula, and I'm going to skip out the state symbols and the use of H2O as the base to remove it, but that's what would be doing it in aqueous solution. So we're going to remove a single H plus, and we're going to left with H2PO4 minus. Now if we write the Ka expression for that, would be H plus H2PO4 minus over concentration of H3PO4, and that one there is going to be 7.52 times 10 to the minus 3. Moles per decimeter cubed, or a pKa value, which I'll just put down here, 2.124. So that's the first ionization. The second ionization starts with H2PO4 minus, and it's that would lose a proton, in this case to make HPO4 2 minus, and we can write a separate equilibrium constant for this one. So Ka2 is again a single proton being lost. We left with HPO4 2 minus as its conjugate base, and the conjugate acid here is H2PO4 minus, and that one there would have a value of 6.23 times 10 to the minus 8. Or a pKa, in this case, of 7.206. And the third ionization event, I will leave you to pause the video and see if you can write that down, both the equation and the expression for Ka and the pKa. Well, let's see how you got on. So you need to start with HPO4 2 minus. You're going to remove a single proton from that, and you're left with PO4 3 minus. The Ka3 expression would be H plus on the top PO4 3 minus, and HPO4 2 minus as the denominator. And the value of that turns out to be 2.2 times 10 to the minus 13 moles per decimeter cubed, with a corresponding pKa of 12.66. So, what do we notice from this? So that was the definition. But one interesting factor is that, as you can see probably easier on here, that the more you ionize, the smaller the Ka becomes. Or, the more you ionize, the more positive the pKa becomes. Now, why is that? It's getting harder to ionize the second time and then the third time, much like ionization energies. Well, the explanation is very similar. Think about the first dissociation with this pKa value, so this is the strongest one. What's going on here is water is going to come along and with its lone pair of electrons is going to pick off this delta positive hydrogen. So this water molecule here is going to come along and remove that proton. That's what's going on there, and because this has got a partial positive charge, it can remove it. Now when we come to the second dissociation, we've actually already lost one of the protons. In fact, I've removed a different one in this case. So we've already lost one of the protons, and that actually gives the molecule an overall negative charge. So we've got over here, this molecule is actually negative already. Now that doesn't mean that these hydrogens here are not, and indeed that one isn't, delta positive. These guys are going to be delta negative. But when a water molecule comes along now to remove another one of these protons, then when it attacks the proton, it's now trying to pull away something positive from a species that is already negatively charged. And that is going to be much, much, much more challenging. So that's basically going to make it much, much harder to do that, much less likely, and therefore the pKa is more positive. We're going to have an increase there. So let's just summarize. Removal of each proton in a molecule will have a unique Ka or pKa value. Each Ka value corresponds to the loss of one H+, so they're separate ionizations. And removing the second and third protons becomes harder, so Ka is going to decrease and pKa is going to increase, even if they, and by that I mean the H+ ions, are identical to start with. And the reason for that is that it's harder to remove an H+ from an increasingly positive species. Sorry, an increasingly negative species. Please forgive me. So as the conjugate bases gain a more negative charge, it's harder and harder to remove that positive H. Now, final point is just a comment on molecules with non-identical hydrogen atoms. So, for example, this molecule here has two non-identical hydrogen atoms. So you need to consider the functional groups present in such molecules. Or another way of putting that, you need to consider the chemical environment of each of these protons in order to decide which will be lost first. Now we've got a carboxylic acid first here, so this is going to have the lower pKa, that turns out to be 2.97. And this proton here in a phenol functional group, it actually turns out to have a pKa of 13.82. But it's important to understand here that the 2.97 does start out with the neutral molecule. The 13.82, yes, a phenol proton is less acidic than a carboxylic acid proton, so that will be lost second. But this value here is higher than it would be in just, say, a molecule of phenol, because you're taking it away in addition from a negative ion formed at the carboxylate group here. So This is always for the removal of one proton in the context of the rest of the molecule, and that may already be negative based on what other protons have been removed.